here goes a solution video for the garbage collection exercise from the 5th lecture. This is not the place to go over again what mark sweep garbage collection is and how it works. For that, see the lecture or see the relevant section of the textbook, which also explains this. But let's go over the exercise just to refresh our memories. The CS61 exercises fundamentals X directory contains a program called nogcbench that benchmarks a dynamic allocator, m61gc.c. Nogcbench allocates an array called chunks, which can hold pointers to k chunks of memory. Then n times it frees a randomly chosen chunk and allocates another one. Finally, it frees all chunks in the chunks array and exits. Okay, so let's watch that happen. So I run nogcbench. Okay, looks all right. We allocate a bunch of things. Printed at the end, 0 allocations. Just to validate that, in fact, it does free all of the memory it allocates, I'm going to run it again, but because Valgrind is slow, I'm going to ask it to allocate to go through many fewer rounds of allocation. So 10,000 rather than 1 million. Okay, heap summary in use at exit, 0 bytes and 0 blocks. That sounds like there are no leaks. Let's look at the code. So the code for nogcbench is located in this benchmark function. And if we look into the benchmark function, we can see first one allocation. We're allocating a char star star, which is a pointer to a char star pointer, or a pointer to an array of char star pointers. How can we tell whether this is a pointer to a pointer or a pointer to an array of pointers? Well, we look for a multiplication in the argument to malloc. There is one. This is an array of k char stars. That's what we're allocating here. We set all of those k char stars to null. I want to point out that double pointers can be a little bit confusing. So a good way to figure them out or to get practice with them if you're not used to them is to sort of write down what the types are and draw pictures of where the char star is, where the array is, and what a char star is. Then here's the big loop that runs n times. Each time we pick a random slot. Interesting, it looks like we actually look at that slot. So we check that that slot's first byte is 62. So chunks s is a char star star. So chunks s is a char star. So it's an array of characters. And chunks s bracket 0 is the first character in the array of characters pointed to by chunks s. Okay? So we first check that chunks s0 is 62, then we assign chunks s0 to 61. That looks like we're sort of detecting whether a particular piece of memory is allocated or freed. We then free chunks s and then allocate some new space into that slot that we just freed, assigning its first byte to 62. Once those n allocations are over, down here, we check that they're all actually allocated, and then free them all. So by check they're all allocated, I mean we check that their first bytes are 62. Okay? So gcbench, our problem set says, does the same thing, except it doesn't call free. And if we run it, it just crashes. Why does it crash? House GDB. Where does it crash? It crashes at this in line 30 of gcbench. It's assigning chunks bracket s bracket 0 to 62. Why would that crash? Well, let's print the value of chunks bracket s. It's a null pointer. So our allocation failed. That's why we're crashing. So if we look at gcbench.c, we'll see here that this looks pretty similar to what we saw before in nogcbench.c, except I don't see any frees. Let's verify that that's the only difference between the files. To verify that, we'll use a very useful program called diff. So diff takes roughly 3 arguments. It can take more, but here's the 3 arguments we usually give it. First, -u. That makes the diff look pretty. Then we give it 2 files, a left-hand file and a right-hand file. so here I'm going to give the left-hand file as no gcbench and the right-hand file as gcbench.c. If I just run the diff, it'll dump a bunch of output onto my terminal. If I want to gradually page through that output on the terminal, I need to take that output and hand it to another program. That's this pipe operator right here, the vertical line. So I'm giving a pipe operator, and then I'm saying, take the output of that diff program and give it to this less program, which is a useful paginator. So it's a paginator because if I press space, I go to the next page. If I press B, I go backwards. Very useful. So how to read a diff? There's 3 kinds of lines. Well, 3+ kinds of lines. But in the main body of the diff, there's 3 kinds of lines. Lines that start with a space are the same in both files. Lines that start with a minus are only in the left-hand file. And lines that start with a plus are only in the right-hand file. So at the top, we see what those files are. The minus, minus, and plus lines tell us where those files are. And then these context lines that start with at tell us what line numbers are the snippet below comes from in both files. So here, this is telling us that the line M61 free is only in the left-hand file. In other words, gcbench.c removes it. Similarly, these lines, these M61 free calls, are only in no gcbench.c. And diff has told us something else that's important, which is that those are the only differences in the benchmark function between the 2 files. So in fact, they're identical except that gcbench doesn't free. All right, enough of that. Let's actually work at creating our garbage collector. So all the places you'll modify are in m61gc.c. Here's an explanation of Mark Sweep garbage collection. This section of the book, 9.10, might be useful for you. At a high level, the GC examines all of memory and finds all active allocations, and then frees all inactive allocations. So here's our work. First, we want to modify M61GC to unmark all active allocations. Use the marked member of the allocation structure. Okay, let's take a look. Here's the allocation structure. It does have a marked member. It's an int, so probably, can have integer values. But in this case, we're only distinguishing 2 kinds of allocations that are unmarked and allocations that are marked. That's a Boolean. Let's use unmarked 0 and marked as 1 for this marked member. So how are the allocations stored? Well, they're stored in an array, not a linked list. And here is that array. So there's a pointer to an array of allocations, Alex. Then there's a number of active allocations, nAlex, which is the number of allocations that are currently active. There's no linked list here like you might have had in your problem set, just the array. Great, good to know. Let's go down to the M61GC function. Here's that function. And the first place that we're asked to modify is here, where we're going to unmark all active allocations. Okay, so we have an array of allocations. We want to unmark them all. To unmark an allocation, we set its marked member to 0. So this sounds like the job for a loop. So let's write a loop. nAlex is the number of elements in the array, and each time we just say alexi marked equals 0. That should unmark all allocations. Fortunately, this is not good code. This is not correct. So let's take a look at what the compiler says. I is undeclared. Okay. In this class, we often use mixed declarations in code. So let's put that type of int I right there. Int I less than nAlex. Okay, I've made good progress. Warning, comparison between signed and unsigned integer expressions. Okay, so this is only a warning, it's not an error. We could move on and ignore this, but we shouldn't. You should pay attention to every warning and fix them when you can. If you can't fix a warning, you should come and talk to us and we'll help you fix it. Okay, so comparison between signed and unsigned integer expressions. That's saying that this comparison, I less than nAlex, one of the operands is signed and the other is unsigned. In this case, I is definitely signed because it's a signed integer. So that says that n_allocs is unsigned. So it's generally a mistake to compare signed numbers and unsigned numbers because there are some bit patterns that in unsigned numbers are very large, whereas in signed numbers they're very small, they're negative. So in general, if a value can never be less than 0, then it should be represented as an unsigned number. And this warning is telling us that this index into the Alex array can never be less than 0. All right, so what type should we choose for I? You might think that unsigned would be a good answer, and it would, but there's a better answer. The type of I should be the same as the type of n_allocs, and this is because we're comparing them. If we have a different type for I and for n_allocs, then perhaps the type we choose for I will be too small. And if n_allocs got really big, for instance, if it was more than 2 to the 32, then this loop would break. In fact, it would run forever. Okay, so let's take a look at what type n_allocs actually is. n_allocs is a size t. So since the bound of our array size is a size t, our index into our array should also be a size t. So let's make it a size t and see if we can't make further progress into our compilation. Next error, invalid type argument of arrow, we have an allocation. What does this mean? Well, the arrow operator requires that its left-hand side be a pointer of some kind. The arrow operator dereferences that pointer and then modifies the structure or union that is pointed to by the left-hand side. So in this case, we're not giving it a pointer, we're giving it just an allocation, a struct allocation. So this is not a case for the pointer, this is a case for the dot. All right? Very good. We've now successfully unmarked all active allocations. Our next step is to complete mark allocations. So if a valid pointer is found in the indicated range of memory, mark that allocation, and additionally check its contents for more pointers. Hint, check out find allocation. Okay? There's mark allocations. So what we want to do is we have an array of memory, and it might contain something like this. And what we're looking for is a value that happens to equal a valid pointer. So it's an interesting thing to point out here. We are going over this memory a byte at a time. So that means that first we're going to check the first 8 bytes of memory to see if they contain a pointer. Then we're going to check a partially overlapping 8 bytes of memory, and so forth, every time advancing by 1. Why are we doing this? Couldn't we just do it like this? Check the first 8 bytes, then check the following 8 bytes, then the following 8 bytes after that, etc. Well, we could probably do it either way in this simple program, but the advantage of doing it 1 byte at a time is that if the compiler was really sneaky and stored a pointer at an unaligned location, or if the user was sneaky and did the same, essentially took a pointer value and misaligned it, we would still find that pointer value even though it was misaligned. Okay? But interesting to note that that is how this loop is working. Okay, so I'm not entirely sure how to get the data at base plus I, but let's say that we actually got it somehow and stored it in this PTR variable. What will we do with that PTR variable? Well, we want to check whether PTR points to an active allocation, to a live allocation. And for that, we need some function that takes in a pointer and tells us if that pointer is inside a currently active allocation. We have that function already. It's find allocation. I'm not going to show you the code. Notice how little we've looked at the other code in this file. I'm sort of zooming out and only trying to understand this file as much as I need to get my work done. It's probably not a good way forward to try and read the entire file at once and put it all in your head. Instead, sort of browse around, use our hints, look for what you need. When there's a head comment on a function like this, which is a specification for how that function behaves, read the specification and believe the specification rather than trying to understand how the code does what it does. Okay, find allocation pointer returns a pointer to the active allocation containing this argument, or null if no active allocation contains that argument. Interesting. So here's how I might use that function. So I call out to find allocation, pass it the pointer argument, and if A is not null, then A is live. We should mark it. That's not all. We also need to look inside the data at that allocation to look for more pointers, because the job of a garbage collector is to find the transitive closure of all live memory. We're not just looking for live memory pointed to by the stack, we're also looking for live memory pointed to by live memory pointed to this by the stack. So the stacks, the pointers that are pointed to by the stack, plus the pointers that are pointed to by those pointers, plus the pointers that are pointed to by those pointers, plus the, and so on and so forth, until we reach closure, until there are no more allocations defined. So how do we look inside this allocation for more pointers? This is a recursive call to mark allocation. And what arguments do we give it? Well, we give it a base and a size. The base is the first address to look for pointers in, and the size is the number of bytes. Well, guess what? We already have those. Struct allocation tells us the pointer to the first allocated byte and the size of the allocation. So if we go back to mark allocations, we just pass in the pointer and the size. Okay, we're almost there. The last thing that we need, hopefully, is to find the data at base plus I and put it inside of this char star. Now I'm going to write this in a way that I don't think I saw anybody else do, but this way of writing that requirement is kind of makes it very clear what's going on, which is I'm going to use memcopy. Memcopy is a function that copies memory from one place to another. We want to check if the data located at base plus I contains a pointer. So let's copy the data at base plus I into my PTR variable, and then the PTR variable contains a copy of the data at base plus I through base plus I plus 7. And that copy sort of makes it very clear that we're taking memory and putting it in and using the 8 bytes of memory and treating it like a pointer. Okay? Hopefully you see how this makes things quite explicit. And this is in fact how the solutions code is written. But there are other ways to write this code. Let's experiment with one other. And this is a mistake that we saw a couple times in class. So check if the data at base plus I contains a pointer. I said pointer plus I meant base plus I. Okay. What do you think the compiler is going to do with this? Compiler complaineth. It says initialization makes pointer from integer without a cast. Okay. So what does that mean? Well, we have a pointer variable that we're initializing. We're making a pointer through initialization. This is saying that the value on the right-hand side, star base plus I, is an integer. So when the compiler says integer here, it doesn't necessarily mean an int type. It just means something integer-like. An int, a short, something else. Well, what is it? Well, maybe this will help. Star base plus I is the same as base bracket I. Those are exactly equivalent expressions. Base is a pointer to character, so base bracket I, or base star base plus I, is a character, okay? So what are the possible values that a character can have on XA664, negative 128 through 127? None of those values are going to be pointers, okay? So this is not actually doing what we want. We're not taking the data located at base plus I through base plus I plus 7. We're not taking the pointer contents of those values. We're just taking the single byte at base plus I and pretending like that's a pointer, okay? And that will never work because we haven't loaded enough bytes. We can shut up the warning by adding a cast, but we still won't have solved the problem because now this char star variable, I'll just show you that it in fact What a useful warning. Cast to pointer from integer of different size. Okay, so I thought I would shut up the warning, but I didn't. Thank you, compiler. The compiler is telling me that this expression on the right-hand side is too small to possibly contain a pointer. In other words, it has the values negative 128 through 127. A pointer variable is 64 bits big, not 8 bits big. Okay, so we need to find a different way. Let me just skip to the end and show you what that way is. Okay, this is the way to load a char star out of the memory starting at base plus I. So what are we doing? We're taking an address, base plus I, which is the address where you want to find the pointer. Then we're casting it to a pointer, char star star. When we dereference that value, the char star star, what do we get? We get a char star. Okay? So if I compile this, no warning. So this and the memcopy mechanism do the same thing. In some ways, the memcopy mechanism might be easier to understand because it sort of makes it explicit that we're treating the base array as just raw memory. Okay. There's some foreshadowing here. So try and figure out what's wrong with that code if you can. Finally, free unmarked allocations, your code here. Okay, so we're going to free unmarked allocations. Well, we know what kind of loop to write. For size di equals 0, I is less than nallocs plus I. How do we know if an allocation is unmarked? Well, that's true if allocs marked equals 0, because all the other allocations have been marked. And what should we do if allocs marked is 0? Well, we should free allocs I. Okay, so here's an incorrect thing to say. Why is that wrong? Allocs I is not the memory that was freed. It's a pointer into an array. Okay, so we shouldn't free something that's in the middle of the array. Probably the easiest thing to do here is just call M61 free. The advantage of calling M61 free is that M61 free not only frees the memory that was allocated, which is stored in alloci.pointer, but it also cleans up the allocs array, shrinks it, so that we're no longer referring, so that the active allocations array is correct, that it only contains active allocations. Okay, there are two bugs in the code that I've shown you so far. Can you see either of them? Both of them? Let's see how this works. We're running GC bench. We're running GC bench. Okay, we allocated 100,000 things. Good. We're running GC bench. Weirdly, my cursor stopped flashing. I seem to have stopped making progress. I wonder what's happening. Could wait forever. Chunk allocation 200,000. Okay, great. So this seems awfully slow to me. Doesn't it seem slow to you? Let's see if we can't figure out why this is slow. So is this going to be slow? Probably not. We're just going over all the allocations. Is this going to be slow? No, this is also O of nallocs because we free once per allocation at most. Mark allocations, on the other hand, might be slow. So we could use GDB to try and debug this. What I'm going to do is I'm going to use printf. I'm going to say when we start a GC, we're going to print out a little GC note. And then when we mark a particular range of memory, let's print out that we're marking that memory. Base size. Okay, I'm going to make and run GC bench. Okay, we have a lot of noise there. So I'll, again, pipe to less so I can see that noise. Okay, we run GC. Okay, it looks like we're finding a lot of memory. looks like we're finding a lot of memory. Okay, how can I tell whether this makes sense? I'm seeing that I'm allocating all of this memory, that I'm touching all of this memory, but maybe I'm printing out too much data. Maybe instead of printing this out, I should print out some summary statistics. That seems useful. So what I'm going to do is I'm going to add a static size t variable that just tells me how many times I've marked. And I'm going to increment unmarked every time mark allocations get called. So we'll reset unmarked to 0. And then here, after we do the mark allocations, print unmarks. So what's the maximum number of marks we should see? Well, we have one chunk array, and then we have up to, how many chunks? I forget what k is. That's defined in gcbench.c. Okay, so 2048. So I should expect at most 2049 marks, because that's the number, that's the number of chunks we have allocated. Let's take a look at what happens here. So we're GCing, marked 4,105 times. GCing, marked 4,113 times. Why would we mark more than 2,048 times? Can you see the problem? Here's the problem. We're marking an allocation even if that allocation is already live. We might be remarking an allocation, okay? So we should call mark allocations recursively. We should never repeat our work. We should call mark allocations recursively only if an allocation is not already marked. Let's see what this does to our numbers. There we go. Now the mark phase is running a little bit faster because we're marking only roughly 2049 times. So these are more than the 2049 that I said was the bound. Perhaps some of these extra marks are just from random values that look like pointers that happen to be located on the stack. Okay, we're doing a lot of GC, but things are working through. Cool. Really doesn't seem like I'm running out of memory. This is too slow for a solutions video. Let's shrink the number of times we call the GC. And take a look at how many. Ooh, this is no good. Running this again, I'm piped its output to less so we can look at its output. When I exited, there were 33,967 allocations. So there was a lot of freed memory that hadn't gotten freed by my garbage collector, even though I was marking roughly the correct number of allocations. What's going on here? This could be a tough one to debug. So it looks like we're not freeing everything that we should. Why might we not free something? This is a tough problem to solve unless you actually look into the implementation of these functions. So let's take a look at the implementation of M61 free. What does M61 free do when it frees an allocation? So we find the index of the allocation to remove. That indication must match pointer exactly. Then we remove allocation from the array and free it. So the remove part is interesting. We have this array that looks like this, A, B, C, D, E, F, G, and if we are passed in pointer j, then that move is going to do this to the array of allocations. So we remove j from the array, and then we move all the other allocations down to fill up the space located by j. That's what the move does. Okay, so let's try and test some theories. So one theory we might have is that free is never getting called. So to test that theory, I'm going to add a call to free. So if free is ever getting called by RGC, we should see those calls. Okay, free is definitely getting called by RGC. RGC is doing a good job at freeing lots of allocations. It's just not freeing all of them. Let's do something else. This is a sort of a debugging, I'm trying to give you some debugging tools. So let's print the ones that we should free. So rather than intermixing free and print, let's just print first all of the allocations that we should free. If alloci.marked equals 0, then print should free %p. We'll print that pointer value. And here, when we do free it, well, we've got a printout that says that we freed it. So if everything is working as we should see a bunch of should free lines, and then we should see a bunch of free lines, and there should be one-to-one, a one-to-one mapping between should free lines and free lines. So just to verify that, because we know there's going to be a bunch of printouts, let's add some counters. So I'm just going to, n unmarked and n freed. So every time we see an unmarked thing, we increment n unmarked. Every time we try and free something, we increment n freed. And let's print them both out. Unmarked %e freed and unmarked and freed. Okay, we have a bunch of should free pointers, should free values. Scan, 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 scan. Call free. Okay, then we have a bunch of call free markers. Okay, I press Control C too soon. We'll scan that. What I'm about to do now is to ask less to jump forward to the point where it says unmarked. So it's thinking, thinking, thinking. Interesting. We saw 63,000 unmarked allocations, but we only freed 32,000 of them. So it looks like about half of our should be freed allocations were not freed. Gosh, why? What's going on here? Maybe if we go a little more granular, we'll understand. Okay, so here's the values that we should free. And I'll just copy these into the other window so we can get a look at them. Okay, so those are our should free values. Now we'll scan forward to the called free. Let's compare. OT20 2BO D4O, O20 A2O 2BO. Okay, so we skipped this one. Then we got this one, but we go from 2BO to D4O. 2BO, EBO, we skipped this one. Okay, so after D4O, we should go to 1EO and then C4O. We go straight to C4O. We are skipping every other allocation that we should free. And why would that be? The The answer is sort of staring us in the face, and yet it's hard to see. Here's what's going on. When we call M61 free on a particular allocation, allocs shrinks. And, importantly, the slot that's occupied by I is reused for another allocation because the rest of the array has been shifted down into the spot that we just freed. Okay? So we are skipping every other allocation because we're freeing an allocation and then another allocation is moved into its place, but we just skip over it without even checking what it is. The very simple way to fix this is this. So we want to reconsider the slot because it has a new allocation in it. Has a different allocation in it, I should say. Let's see what happens when we run this code now. So marked 2059 times. Scanning ahead to my printout. 63,478 unmarked, 63,478 freed. Okay, we are now freeing every unmarked allocation. With that, we can get rid of some of these debug printouts just to make everything run faster. And take a look at the output of our GC bench program. We're running GC once. We're running GC again. And at the end, we have only 5 allocations that are allocated. Okay? This is literally the end of this exercise. So how much code did we actually write? Well, not counting all of the debug code, here's the difference. Well, counting all of the debug code, the difference is this. 1, 2, 3, 4, 5, 6, 7 lines, not counting the comment. 1, 2, 3, 4, 5, 6, 7, 14 lines total for your debugging memory allocator. That's for your garbage collector. Pretty cool.